just to break the ice a little bit, the first thing that everyone asks us here is, who are you? What are you here? What is Pure Storage? So my hope through this talk is I want to tell you some of the cool things we are doing internally as an engineering team, regardless of whatever we do with big data analytics. How are we solving our own problems of continuous integration at scale? We test, running a lot of tests and making sense of them. And then I also want to break into how using our own storage platform internally, we run our own data center, has helped us reach this scale with a lot of ease. So I'm going to be talking about some of the common pitfalls that we've observed from talking to our own customers and about how they run their big data analytics projects, pipelines, and how we have not had some of those problems because of our platform. Cool. So let's get started. So at Pure Storage, we strive for excellence, right? It's like that's the goal. Everyone wants to be great. Everyone wants to ship code with no bugs. So from the very beginning, when we were just a handful of engineers and we were building this system, which is a distributed system, it's a storage platform, we made a very heavy investment in automated testing. And it served us really well when we were at a small size. We were a handful of engineers. We didn't have that many prototypes of our own product. We were still iterating through different versions. It's a piece of hardware. So it's expensive to get different versions, so we only had limited numbers. And then when you're testing out a storage platform, you have to have clients that are driving the actual load on your storage platform. So we didn't have that many of those. And additionally, we had a single code line, right? It was all of the code. There was no branches. There were no different feature development paths or anything. So this served us really well. We had hundreds of tests. The moment a developer would add new code, we had a failure, a human would quickly be alerted via email, very, very sophisticated alerting mechanisms. And somebody would take a look at it, and we would, figure out what was the problem and quickly address it. That was our goal. You introduce a bug, you quickly get notified, you quickly go fix it because you still have all the context in your head of what the code that you just added is. So what's our work today, right? We are now 3 years into the development of this storage platform. We have over 100 software engineers, right? We have over 170 FlashBlades. We just installed 50 more in the last month. So FlashBlade is the product that I've helped build and the product that I'm going to be telling you a little bit about today more. So we want to test these FlashBlades. To test these FlashBlades, they're very fast storage boxes, so we need a lot of clients to drive throughput. So we have over 1,000 VMs that all they do is just try to write and read and access the data from our storage platform. We have over 400 clients that are just bare metal machines. We also have some simulations. We simulate our hardware in software. Each of the pieces of this hardware is expensive. We can't just go buy thousands of them. There's this thing called NAND shortage, which is causing, we can't just go build as many as we want. And in addition, small teams work better for software development. So we have over 20 feature branches. That means that we have 20 parallel tracks of code that are being developed at any given time. So a lot of variation has changed now. In addition to that, our heavy investment early in automated testing, kept going. It was part of the culture. So now we run a lot more tests, right? We've scaled from hundreds of tests to over 20,000 tests every single day. Now, think about this. These are tests. These are not the tests that we do when we're releasing code out to the world. These are tests that we do as we're developing our software. So what this means is that bugs are expected, right? Humans are developing the code, and the bugs are going to be introduced. The test spans so many different areas that a given bug may not just break one test anymore. It may break 10, 15, 20, 100 tests. And we're constantly running these tests against all of the versions of our software. We have over 20 different feature branches. So on a normal day, we will have 1,000 test failures, right? It sounds really high, but it's really just 5% of all your tests. So it's not very much. Now, each of these tests has a complicated path, right? You have the test itself that somebody wrote. It's a piece of software that sits on top of our testing infrastructure, which is the way that we deploy these tests. That sits on top of Jenkins, which is the testing coordinator that does the scheduling for our resources. Now, Jenkins is spawning a process in some client that is initiating load that is talking to our storage platform through the network. I just named like 8, 10 different pieces. So any one failure in any of these processes, like say your DNS server goes out, it can cause hundreds of failures, just one problem. right? So we are averaging about 10 minutes of time to just understand why a test failed. Now, if you have 10 minutes per test failure and you want to take a look at all of these 1,000 test failures, you need 20 full-time people. And to be honest with you, most of the large engineering organizations out there are making that investment. They are going and hiring 20, 30% of their engineering workforce to be in QA. We don't have that. We have 5% of our engineering workforce. So we have 100 plus engineers, actually less than that. We have 4 people full-time doing our QA of our testing to go and root cause an issue. So, but as I just mentioned, a single test, a single underlying cause can cause a lot of problems. So to make things worse, we're planning, our product is, happy for us, it's become very popular. So there's a lot of feature requests, a lot of our customers want more and more things, so we're ramping up our development really, really fast. So we're planning to grow all of these 2x in the next 12 months. So that means we're going to be talking, these compound, right? These are not just, we're not just going to have 40,000 tests a day. You double the engineers, you double the VMs, these are compounding. So we're talking about, 100,000s of tests at this point. So we can't scale the human factor. So we wanted to build a system that would help us solve this problem, right? Remove the human effort as much as possible. We wanted to, one of the requirements for this system was to automate the triaging of failures as much as possible. The moment a human root causes an issue, a single test failure, no other human should ever have to go take a look and find the same root cause for another failure. So how do you encode these root causes, right? Can you create, we call them fingerprints or signatures that will identify a root cause? And remember, I told you, they're coming from many different parts, so you need to be able to understand and encode what each of these different parts of our testing are doing. We also wanted to extract performance metrics from the logs. Like any other piece of software, we test the crap out of it. We push it as hard as we can so that when we release a new version of our software, we make sure that we don't regress in performance. Because, right, you have a version of the software and I give you an upgrade and we're suddenly slower. You're not going to be happy as a customer. So we have those tests. But additionally, we have a lot more tests that are just putting our products in very weird scenarios. And we're simulating hardware failures. You're putting our product sideways, upside down, whatever. We're doing just things to try to figure out every single possible corner case that we could ever be in. So why should we not be tracking our performance in all of these weird scenarios as well? We wanted to do that. We wanted to save our logs for future use. We're paranoid. I think everyone wants to do that. Everyone just wants to collect as much data as possible. But one of the things that we quickly realized was there's some bugs that are like really just hidden there. And somebody might have written the bug a long time ago. And only when you touch and tickle the system in some other way, this new bug presents itself, and it now causes problems. So there are going to be cases where we're going to want to go back in time and search through our logs for the last 6 months to figure out when it was a pattern first introduced. We wanted to do this in a scalable system, right? As I said, we're growing, exponential growth, more tests. So we needed a system that will be able to easily scale as we scale our people, our infrastructure. And we wanted real-time results. This one was fun. We wanted, if you have a failure somewhere in your pipeline, essentially, of our testing, we want to be notified as quickly as possible so that a human can take action, so that you cannot have this cascading effect of test failures that can essentially blur your view of how well your code line is doing, right? So we tried a lot of things, a lot of the open source technologies, and I'm going to be talking to you about right here about what we settled on. And if you have any questions about some of the things that we tried, I would be happy to talk to you about offline about different other technologies that we tried and failed at least quickly and easily doing this. So most of the infrastructure uses Logger. Our own product uses Logger to save our logs. Network can be easily hooked up, same with clients, same with testing. So we already had Logger, so we decided to go with rsyslog. Rsyslog is just a remote syslog server. All it does is essentially sitting in a port in some machine somewhere, and it's just waiting and receiving messages, right? So what we've done is we've created connectors from every single piece of our infrastructure to send all of our logs to rsyslog servers. Now, the job of the rsyslog servers is twofold. One is to save all of our logs. We've now brought all the logs to a centralized place, and this is the time when we save them for our future use. Additionally, we're going to be building a streaming pipeline, which means that each of the lines of the logs from all of these different parts of our testing need to be uniquely identified by the end, so that when a pattern is identified on the other side, I can go back and trace exactly what FlashBlade was running on, what test was being run on, what code line, what SHA of our code was being tested. From our syslog, then we pipe and send all of our logs to Kafka. The reason why we picked Kafka is we originally didn't have it. We would just send it directly to a compute engine that understood what our signatures were. But we quickly realized, of course, we're writing code again, and we fall into this similar pattern where we're introducing bugs in our code. So if you have code, if you have bugs in the code of your processing, then the processing may fall at any time. So we needed this resiliency layer in between where we know we have all of the logs and our processing engine, which we use Spark for. So Kafka, again, just a broker. If Spark ever goes down, especially early on as we were developing our platform, Kafka just makes sure that you can go back in time and pick up reading from wherever you left off. You can also, based on how long of a policy you have for Kafka, you can choose to have it 3, 7 days, 15 days of storage, and you can go back in time and quickly scan through those based on the Kafka offsets very, very easily. Right? From Spark, we do something very interesting that I don't think a lot of people do because I think generally people are afraid of. But we use the file system metadata to do our indexing. So this is the time where we understand a failure. So Spark is essentially, you can think of it as a really big filtering job that is constantly running 24/7. And we feed it data from a database that is not shown here where people are writing their signatures, their patterns. And Spark is filtering and using the metadata of the file system, whether that's NFS or S3, to do the indexing of when it happened, where it happened, what test it was running, based on just, you can think of directory structures. Spark is also extracting all of our performance and sending it over to an Elasticsearch. That's just, one of the other goals that we wanted to do. And it is also sending events to a Kafka queue once again. Kafka here again, same purpose, just make sure we have resiliency in our pipeline. From Kafka, we're doing some post-processing. So this is a little bit interesting, right? Our most common pattern is that a single log line from somewhere in our infrastructure, from all of our logs, can identify a failure. That problem, we found empirically that it took about 75% of our root causes. You could encode them with just a single log line from somewhere in our pipe, right? Whether it's the network or the storage or the clients or the test. But there are more complicated root causes where you need to have multiple events happening in different parts. The network goes down for half a second, and the storage hiccups for milliseconds, and you need to be able to make sense of all of these. So our post-processing layer, in the most simple case when the signature is identified by just one event, all it's doing is saying, yeah, the event happened, I'm going to ship it to the reporter. In other cases, it's waiting for more events because some of these encodings of these events have to be seen as a group and not just as a single event. So the post-processing is happening here. Now, because we have Kafka, it also gives us a really easy way to have a distributed system. The post-processing is really, you can think of the engine being 100 lines of Python code, where all it's doing is just a consumer reading from a different topic of a Kafka queue. Now, our Kafka queues happen to have 200 partitions, so we can have as many as 200 different Python processes in 200 different machines, and we can scale the compute that way very easily. If we need to do that more, we can just add more partitions to our Kafka topic for this one topic. Post-process, again, is the most simple case, also pushes to Kafka, and we've built, again, very simple Python connectors to all of the places that we want to report to. So the most common ones that we do are Jira, Jenkins, and Kibana. Kibana is just sending, hey, run this query because I want to generate this graph so that somebody sees what is happening to our performance. Jira is our engineering tracking system. So the moment there is a bug somewhere that somebody finds, they go and open a ticket, right? And they assign it to some team, the team that was in charge of developing that part of the feature. Now, Jira is the perfect place for you as a developer to understand where all the places and what are all the scenarios that your bug is causing problems. So that's why we're using Jira to report this. We've added some scripted fields, and Jira now, as it loads a bug, a ticket, it pulls all of the data from our internal database that we're pushing into, and it's just loading and saying, these are all of the hits that you have for your pattern. It's happening in these branches. It's happening at this time in these certain types of versions of our product, right? So we also have a lot of different versions of our product. Jenkins we use for just figuring out how well are we doing in triage of our failures. So we have reporting based on Jenkins that says, if we had 1,000 failures today, how many are identified and mapped down to a root cause? That is important to us, right? Because we made a really, really heavy investment in this automated testing infrastructure. But what good does it do to you as a user to run 20,000 tests if you cannot look at all of the failures? It's just wasted effort and wasted money because we're running all these cycles, right? So this is our pipeline. So what does the pipeline look in terms of infrastructure, right? Again, so everything on the left is sending, and capacity-wise too, is sending about 6 terabytes worth of logs. So these are being shipped per day. These are being shipped real time as they're being generated by all of the infrastructure on the left. Now, our syslog is creating semi-structured data. So it's creating JSON from each of these log lines and amending it with information from where was the log line happening. Is it coming from the network? Is it coming, and what test was it running? What SHA of the code was it running? So all of these details so that it can be uniquely identified on the other side. So this is one of the steps in the pipeline where the data explodes and grows. So now it's 3x, it's 18 terabytes of data. Kafka is then shipping those 18 terabytes to Spark. And Spark is doing is extracting only about 6 gigabytes, which is all of our performance data. It's doing some aggregation so that it doesn't do like a lot of inserts into Elasticsearch, which we found quickly that Elastic does not like. So it's just a lot of single events. So we're trying to batch them as much as we can in Spark. And Spark is also doing the filtering into our file system. So this is where we use our product, the FlashBlade, right? So FlashBlade is it's a file and object store, a really heavy file and object store that gives you a really fat pipe into your data. So we can provide you with a single 4-rack unit up to 16 gigabytes a second of reads. So Spark is, and provide you a lot of concurrency, right? We've built this system to handle thousands of connections at any given time. So essentially, each one of the Spark cores can write to our file system and have no problems. And additionally, this box can do a lot more than just Spark. So we use it to back all of our infrastructure. So we really only have, you saw in my picture earlier that we use Kafka in multiple steps of our pipeline. But it's just a single Kafka cluster, right? There's no need to have multiple of these, just different topics. And even Kafka is backed by our file system. So all of the intermediate storage for Kafka, we have it set right now for keeping up to 3 days of data. All of that intermediate data, all of the offset management, everything is happening backed by our own storage. So all of these compute nodes, each of these gray little boxes are VMs essentially, and they don't have any local storage. They just have network attached storage. And this is what they're all running on. Our syslog is obviously running to the FlashBlade where we're using to store all of our logs going forward forever, hopefully, but at some time we'll run out of capacity, I'm sure too. And this is what we call the custom code. We talked about the post-processing, where it's about also 6 gigabytes of data per day, which are the signatures and the events that we are finding are happening, right? So the kind of things that we report are, yeah, this is a duplicate bug, or you had an infrastructure failure, this switch went down, somebody should go take a look at it, or you have a performance regression, an engineer should be notified. So we've definitely added scalability in every single step here, right? If you look at everything on top of the FlashBlade, these are very common open source technologies that are easy to scale, and they can be done, like hot, right? Like you can add them as you're running and not have to take any of your infrastructure down. Essentially, if you need more Spark processing because you now have more signatures to encode, you can we spin up another Docker container and add it to Spark. And then Spark just picks up those scores and starts going with it, right? The only real place where we feel like we've ever had to take our pipeline down for some time is when we need to add more partitions to Kafka. And the reason for that is because the number of partitions that Spark is going to be using is limited by the number of partitions that Kafka has to pull from. So that's really the only place where we've ever had to take down our pipeline is to increase the number of partitions. So because we don't want to do that very often, I think right now we have a 3-to-1. It started with about 10-to-1 in terms of partitions to cores of Spark. And little by little, as Spark has grown because of the number of signatures and events that we're encoding, that ratio is going down. We don't expect it to grow very much because, again, these are signatures and patterns that are not long-lived, right? This is during the software development cycle. So we expect each of the signatures to have a lifetime of about maybe 30 days. So it's not super long. So it's not going to grow unboundedly. It's really going to grow based on how many feature branches, how many people we have developing, because there is a human factor to that. So the custom code, as we talked about, very simple Python processes that can just be easily spawned all over the place. So, in summary, what we've done here is we had this problem, right? 20,000 tests, 1,000 test failures. We would have needed 20 people to handle this. What we do now is we're looking through a data analytics pipeline at every single line of logs that are being generated by our infrastructure. And we're identifying, in average, about 30 distinct failures that are being introduced or are happening because of just, shit goes down, right? It's infrastructure. 30 distinct unique things that are happening at any given day in our testing. And now you really need a single person to just take a look at all of them, right? They still we still have 3 or 4 people, but it's really a single person can now do this job and look at all of these failures. So, and now we're breaking into the next step now. We've solved this problem, but now we can do more cool things, right? We have our processing all of this data real time. Now we want to give developers a view into how their code is doing across multiple scenarios. Because a developer today, right, these are pieces of hardware. A developer cannot be assigned a piece of hardware because we can't scale that. So if a developer can write patterns or queries that are looking at all the logs across all of our infrastructure clusters, they want to be able to see pretty graphs. They want to be able to, they're making assumptions, right? We have algorithms like garbage collection, compression. They want to know how well that is working, right? And you can really only get that data by looking at the big picture. So now we're breaking into that where we're adding more value and using all these data that we're processing, not just to solve the problem that we had, but to now give new abilities to our developers. So let's break down into some of the common pitfalls, right? So we were super excited. We turned this project around. Again, these are very standard open source technologies. We turned this project around in about 3 to 4.5 months from when it was a toy project for somebody. And then we were like, this is cool. We need to do this. We're not looking at all of our failures. And we made an investment in 3 engineers, only 1 or 2 that had actual data science experience and some of this infrastructure tooling. And yeah, so it was really cool. We were super excited. We were like, oh, everyone must be doing this. Like, why is not everyone using all these big data analytics tools that are working so well? So we went and talked to our customers, of course. We are a vendor provider, right? We sell storage. And we wanted to hear from our customers. Are you doing this? Why are you not doing this? What are the problems that you're seeing? So let's go through some of the problems that people are seeing, again, from our customers that we've talked to. So scaling compute, right? How does it look like generally, right? So something that we assume that we had to do in some sense, right? We built this FlashBlade product, so we sort of had to use it. We didn't even think of using anything else. But everyone out there, or at least most people, is using HDFS, right? If you are on a on-prem data center, you're using HDFS more likely than not, because this is what just the industry has available. And then you have this HDFS data lake, and then you have these silos of infrastructure for Spark, Kafka, Elastic. And on the right side is what our infrastructure would look like, right? You see there's a very clear separation between the compute on top and the storage. It's sort of going back in time to 15, 20 years ago to very relational database model style of analytics, where you had your big compute servers, which were not distributed really, right? I mean, now you have some distribution, but still not very much. They're not very scalable. And you have this big storage. But now you have these distributed compute clusters with a lot of compute. And as long as you have a storage platform in the bottom that can provide you these concurrency accesses to it, you can go back to that model. And there are benefits to that model. People want to go back to that model because if you want to scale compute, why should you go having to create new nodes that are going to have to pull the data from these lakes, right, and now process it again? Why should you not just be able to add more compute to the clusters you already have? So some of the things that we can do that we found that our customers couldn't do was streaming and batching analytics together, right? So I told you earlier that one of the goals for our pipeline was that we wanted to be able to go back in time for maybe 6 months and take a look at all of the data that we've collected to find the first introduction of a problem, right? So I told you this project hasn't been around that long, so we don't actually have 6 months of data, right? So we only have about 3 months of data. But we did use it. We had 3 months of data. We wanted to go back in time and see a bug that we believe was introduced a couple months ago. We didn't know exactly when. And one of the things that we can do is, because we have the FlashBlade, we can spin up compute dynamically as we need and just, point it to our FlashBlade storage platform. And to spin up all of this, we use Docker containers. You can use, honestly, whatever virtualization you want for your compute. But you can use Docker containers. And we were able to spin up a 1,000-core Spark cluster, targeted at our FlashBlade, and just our FlashBlade gives you the throughput, right, to really access all of this data as fast as you can. And then when we were done, we took it down, and we moved on. So having the ability to dynamically spin up this compute, obviously, you have to have the compute available somewhere, right? But you don't need it dedicated to this use case, because most of the time it's going to be sitting idle. So scaling storage, right? I just told you the problems with scaling compute. Scaling storage is essentially worse. Think about some deployment that you may have of HDFS or Hadoop. You generally have a certain amount of compute based on what you're querying or what your ingest ratios are. Now, again, people are paranoid about keeping data for as long as possible. Say you were keeping data for 6 months or 1 month or whatever, and now you want to keep data for double that amount of time. You have to go buy more compute, and have to buy more licenses of your software, and have to buy more hard drives and hook them up. And it becomes worse, because now you have to wait for rebalancing of your HDFS cluster, right? You have to do some migration of the data. Why should you not just be able to insert blades into your storage platform and just move on? I don't need more compute. I just want to retain more data. Why should I have to go buy compute and install it and wait for all of these migrations and rebalancing? So our value here is that we are taking away that complexity from managing these kind of clusters. We are doing obviously, somebody has to do the rebalancing, right? This is a distributed system. It's scale out. The data has to be spread over all these nodes. But we do that, right? We've invested time, effort to do that really well, and so that you don't have to worry about it, right? And another common one is performance, right? So in this pipeline that I talked to you about today, from the moment a log line is generated on any part of our infrastructure until we alert somebody, is anywhere between 1 and 3 seconds, right? So we do care about performance in our case, and there are use cases that do. Now, HDFS and Hadoop, generally not so much, right? These are some of the assumptions that came about when HDFS came up, right? So HDFS was based on this thing called Google File System. I'm not sure. Maybe some people are familiar with it. But they built this platform based on assumptions from 15 years ago, where the world was different, right? 15 years ago. Imagine how long ago that was in tech, right? The typical file was very large. The access was sequential. You only had hard drives. Like SSDs were not a thing. So you really wanted to have that sequential access. You didn't want to have concurrent access to your hard drive, because the spindle of the hard drive would be moving left or right, and it would just cause problems with your hard drives, right? Hard drives would fail all the time. Not just hard drives. The network was bad, too. It was slow. The network was very slow. So there was this concept of, let's bring the data to the compute, and everything's going to be great. And it was. I mean, I don't want to say great, but it worked, right? It really worked. It got you to have this scalability of, exabyte level data in a time where tech wasn't really up to it, right? So it was cool. It worked. But a lot of these assumptions are no longer true, right? So the data is now different. I believe that we're going through a different change, a different, modern big data analytics, whatever you want to call it, where Hadoop was king, and they had all these technologies that were built on top of HDFS because of Hadoop, right? And Hadoop may really still be your good processing platform, but HDFS has a lot of just problems that you can't get around, like metadata nodes that are bottlenecks, or having to have this multi-tenancy where having no control over your performance. Now, the fact that we're going through all of these new technology change, it's a perfect time where a lot of these technologies are not necessarily built for HDFS. So think about Spark, right? Spark is the best example. Spark was not built for HDFS. It just happens to talk to it, because they realize most people have their data in HDFS. But you don't have to have an HDFS. You can go S3, you can go NFS, you can go whatever centralized file system you want to have. It's also true for all of these technologies in the screen. And these are all the popular things that are coming up and going forward. Again, they talk to HDFS, but they don't have to. So just think about that. The data is different, right? You're not just batching all your files into these massive things. You have small files, large files, you have everything. So hard drives, are obviously a problem. You have random to sequential access. Everyone's hearing and talking about machine learning, artificial intelligence. In machine learning, in the machine learning world, you don't want to have access to the data the same way. You want to have random access so that you don't bias your training. So random access is very important. Real time is a thing. Everyone's talking about it. Streaming, yeah. So, they're just changing the assumptions all over the place. And in the infrastructure world, network speeds have changed a lot. You can access data through the network today faster than what you could access in your hard drive in the same box 15 years ago. So network is no longer slow. Network is not a bottleneck anymore. So this is why we built the product that we've built, the FlashBlade. We believe it's the first true scale-out file and object store for these big data analytics, machine learning, AI kind of workloads. Right? FlashBlade, it will expand up to 75 blades. It can give you up to 80 gigabytes a second of reads performance, and a third of that in write performance. We provide multiple protocols, S3, NFS, SMB, whatever you want to use. Essentially, we built a very large distributed key value store underneath that is resilient, obviously. We have this blade architecture, and any of them can fail. And we've built protocols, access on top of this distributed key value store. So we get rid of all of the bottlenecks that you have with your HDFS cluster. We don't have metadata problems. What do you mean I know limitations? No, those things don't exist because it's just another key value in our distributed system. So scaling is not a problem. Really large file, not a problem. Small file, whatever. Everything works. Our goal as a company and ethos is that we want to take complexity away from you. We want to take that complexity into the design of our system so that you can just worry about doing data science. You can worry about what value can you bring to your business by using your data. So the FlashBlade is essentially just tuned for everything. We don't have tuning knobs, right? Most of the storage platforms out there, you can tune them to do whatever you want, honestly, right? Some knobs here and there, but they won't do everything right. And this is where we believe we add value, right? And why is this important? Because analytics is constantly evolving, right? Look at these quotes from 2011, 2013, and 2015, right? Hadoop, right, the big thing. Then we move over to Spark, and now we're talking about AI, right? And AI is really just another flavor of analytics, right? So AI, let's take a look at an AI data pipeline. What does it look like today, right? You have the ingest, where you have your sensors, your machines, whatever, your telemetry of your data. You have to clean and transform the data. You have some ETL pipeline, some labeling, anomaly detection. Then you're doing exploration on this data, right? If your data set is not very large, you may not using GPUs, but when data sets grow, it makes sense to move over to GPUs. And then you're doing training. So each of these steps of this data pipeline are different and have different requirements on your storage platform. So take a look at this. I'm just showing 4 different access patterns, right? Access pattern is one thing, sequential or random. Then you have the access type. Are you writing or are you reading, right? Different requirements. File sizes. Metadata is really small in the ingest, right? So you want a system that is able to handle large amounts of metadata. You have small to large files in the clean and transform and small to large in any other of the other steps. It really depends. And having the ability to choose how you do your pipeline is important. Why should you be having to build more software in front or another step in this pipeline just to batch your files so that your storage platform can handle it? Right? Your storage platform should be able to handle everything. Concurrency. AI, big data analytics, it's like they're made for us. Like the soul of this system is completely parallel. So yeah, so I'm one of the software engineers that built the FlashBlade. I also currently lead our big data analytics team internally of some of the things that we're doing now. I've moved away a little bit from product development. One of the cool things that just happened actually yesterday, we were just named Best Innovation in AI Hardware yesterday at the AI Summit in San Francisco. So really cool stuff. We have a link here, purestorage.com/analytics. I think we have about 5 minutes for questions. So if anybody has any questions, I'd love to take them.
object key value pair, right?
So I'm not actually sure exactly what part you mean, but I can go back in time and we can figure it out.
I can tell you the slide.
What's that?
I can tell you the slide.
Oh yeah, please.
No.
Oh.
Back. Right there.
Right here?
Yeah.
Yeah, so each line that is coming in from the left from our infrastructure, we're tagging it with metadata. Essentially, we're building JSON, right? It's completely unstructured. We're making it semi-structured with JSON so that each line can be completely identifiable as it comes out, because we're essentially a funnel of all lines, right?
Okay.
Yeah. And they get mixed, they get out of order, and we don't want to have to deal with those problems. So, yeah.
This picture, where you finally store it?
What's that?
Where you finally store it?
The data goes to our FlashBlade platform. That's exactly it, yeah. So it's a storage appliance. It sits in your data center, yeah.
Yeah, can you go to the slide where,
Oh, ignore that.
yeah, can you go to the slide that has, yes, stop right there. So where in that architecture do you do your complex event processing to basically window and aggregate?
That's in the custom code, right? So if I go back one slide, that is the post-processing. So it pulls from Kafka again, and it's just Python consumers.
Because we're looking at that. I mean, we're about to embark on a pretty massive streaming architecture where we have to do complex event processing, where we have to aggregate atomic events together. And we've been actually looking at Spark to do that. But you're saying that you're doing that. I just want to confirm this.
Yeah.
You're saying that you're doing your complex event processing with windowing and all of that inside of Python?
Yeah. So the reason why we didn't want to do it in Spark is because we wanted to have a low latency from left to right. And if you are doing it in Spark, you increase the latency for the events that don't require that, right?
Is it the micro batching?
Yes.
Okay.
Yes. So essentially, Spark is just a big filtering engine. It filters it, and it indexes based on the metadata. And then the
windowing inside of Python.
yes, just yeah. I mean, it's not terribly complex. Don't take me wrong. We're not doing very advanced analysis on the windowing part. It's just essentially time periods and is it happening or not, right? And then you can. We have super users of our system where they really want to be able to parse log lines and make sense out of the numbers in the log lines, and then base this a pattern hit or not based on those numbers and performing operations, doing calculations. They can do that too. So we support multiple patterns. Again, single event kind of identification, multiple event, whether they're happening or not, or whether you have this event and you must not have this event within a certain time period. Or you can just essentially subscribe to events, give us a script, and we'll run it for you. And then you just get all the events that are happening. So.
But you're referring to the time series, but if that's the case, isn't it the really everything based on a storage engine that you have, which is essentially objectized?
Sure, in some sense, yeah.
Right. Yeah. So key value pair, so you can actually be able to window or do any kind of.
But you still, yeah. Exactly, but you still need to wait for those events to come out, right? And because there's no order guarantees through this pipeline, you have to do some.
But you are caching and storing this stuff in every single kind of state.
Yes.
You
yes.
You have.
We have time for one more question.
Forget my question.
Sorry.
I was calculating. Looks like you're doing like 350 million events per second. So what kind of analytics, if it's 50 billion per day? So what kind of like a calculation? Like, do you do like a top end? Do you do join between two different events?
No, essentially we don't have, we can't afford to do joins with the amount of compute that we have, right? So it's essentially each event is just being processed. It's just a big distributed filtering system.
Being processed, do you do aggregation at all, like a sound?
It cannot happen in Spark. It would slow us down too much. Yeah.
Okay.
So that's why the aggregation happens in the post-processing.
Do you have the numbers for that? Like,
I don't know, none of the, but we can find them later. Yeah, if you can come find me, I'd be happy to show you those.
so you bottleneck it by Spark?
Yes,
processing.
exactly.